So good afternoon from the Energy Community Secretariat from Vienna. My name is Karolina Čegir, Senior Gas Expert, and I'm really very pleased and happy to say that we restarted with Methane Mondays this year after running 3 years in a row very successfully. But majority of you know that because I see many familiar names participating. So with this one, just to just to introduce our today's speaker and our today's presentation. So last month we actually see what companies are doing, how to managing to do on-site and top bottom and bottom up measurement and how they are comparing the data. So with this presentation today, we will continue actually talking about that, but from different angles. So from angle of service and technology provider, how they see this quantification, uncertainty analysis, and how to cope with them. So we have Mr. Matti Iriala. I hope that I pronounce correctly the name and surname. From Aeromont, Chief Technology Officer, to present what they are doing and how they see this analysis, how to deal with these uncertainties, which are actually uh, crucial in this moment, because many of you already started with collecting data, with measurement, with on-site, and anyhow this has to be done in line with EU regulation. So here is just a reminder that we started in March. Today is the 7th April, and here you can see the dates actually more or less agreed for the next month. But not to actually wasting more time, I will just stop sharing my part and then to invite Matti to start with his presentation.
Thank you. Thank you very much. Just a second. So I am now trying to.
Yes, it's coming. So
Okay, so now you should have a full screen, I hope.
yes, we have it. So please, Matti, floor is
Excellent.
yours.
Thank you very much. Thank you. Okay, so it's a very pleasure to be here. Today I want to thank you, Energy Community, for having us and having me here to discuss with you on this extremely interesting but often confusing topic of a site level uncertainty assessment. So here I will provide you briefly an overview to Aramon. Who are we, where are we, and what do we do? Also, I will give you an overview to the different type of methodologies that we can use when approaching methane measurements. Then before we actually move into assessing the methane quantification uncertainty, let's have a look on the emission plumes, on how they look like in theory and actually. And then thereafter, we will see how we assess the methane quantification uncertainty for site level measurements. And also finally, a few words on the test laboratory accreditation. What is the meaning of that in this uncertainty analysis perspective? Okay, so starting from Aramon first, briefly. We are a company founded in Finland soon 11 years ago. From the beginning, we started to develop drone-based measurements methodologies and also payload, so analyzer technology, which is light enough that can be carried with a drone. And during the years, the scope of the industries have varied from maritime to process industries, and now the majority of the tasks related to our work is from the oil and gas industry due to the regulation. We provide measurement services, so basically end-to-end service is possible through us. In some cases, we also work through our partners, but as such, we don't sell hardware, but services. Airman holds a certification for ISO 9001 together with accreditation for ISO 17025 test laboratory. And for that, we will discuss more later on. Okay, so the reasons why we are typically measuring at our customer sites are the customers want to understand their fugitive emissions, where they come from. Are they possibly a risk to health and safety? And then, of course, if these emissions can be quantified, this is also done. Typically, the spreading and dilution is also studied in cases where for example, the odors are annoying the surrounding population from the sites that we're studying. Also, the process monitoring is typically one aspect that is studied because the quantification is a holistic quantification and covers full process units one by one. So adjusting processes between the measurements, you can get real-time feedback on how the process adjustments affect the actual emissions from that specific process unit. The regulatory perspective, we are in compliance with the upcoming EU regulation for the top-down measurements. Also, according to EN 17628, which is the fugitive and diffuse emissions from petrochemical industries. It's for the non-methane VOCs, but actually it's very often applied for methane measurements also, as in the absence of a better standard for methane site level measurements. Then we are in compliance with OGMP 2.0 level 5 and also MIQ, both for facility scale inspection and source level. Now, here you can see a glimpse of some of the companies that we work with, and here you can see that the oil and gas is well represented in our current clientele. Good. Now, let's take a look at the methodologies. How do we approach methane measurements? So, it's very common that the work starts with a mapping. And a mapping is done to understand where the emissions are actually coming from, to identify the hotspots that might need extra attention and might affect the measurement planning or the strategy that we have decided to use in the field for the data collection. Emission mapping can be done purely horizontally, or it can be done through the emission fence line monitoring, where for example, tightly built refinery type of environments, we measure in between the units to differentiate which emissions come from which units and so on. This can be further processed to the site level quantification, also section or even component group level quantification, but mainly as an end result, we always come out with site level quantification. Also, the flare efficiency monitoring is part of the spectrum of measurements for methane. And let's first take a quick look on the site level quantification. This we can apply two different quantification methods here. The reverse dispersion modeling or inverse dispersion modeling, whichever way you want to call it. This was the first methodology that we ever tested, whereafter we moved to the mass balance approach, which is not a modeling approach, but a direct measurements. So in reverse dispersion modeling, one needs to know where the source is, what is the type of the source, is it a point source, an area source, or a flare? And moreover, there needs to be some assumptions related to the topology of the source, temperature of the source, the speed of the gas flowing out from the source, and so forth and so forth. So there are typically a lot of assumptions. The mass balance approach is often used instead of reverse dispersion modeling or inverse dispersion modeling due to the fact that it includes no such assumptions. Also, it is a direct measurement of the concentration and wind field, both upwind and downwind of the measurement area or the section that we are quantifying. The mass balance also goes with other names. It can be called the conservation of mass, or it can be called a flux plane, or anything similar to that. In all these cases, the methodology is a direct measurement of wind and concentration, and it is at the end a mass balance approach. For flare measurements, there are several different possibilities, also different outcomes. So straightforward solution is a mass flow rate measurement of methane from the flare. This will result as a simple mass flow rate results. But if that result is combined with processed information on what is the methane flow into the flare, this information can be further analyzed into a methane destruction efficiency results from that specific flare. Also, there's possibility to do a concentration measurement, which is not a mass flow rate measurement for different compounds coming out from the flare plume. So measuring methane and carbon dioxide, also possibly alongside other carbon products such as carbon monoxide or non-methane volatile organic compounds can be joined into the same measurements. The outcome of this measurement is the flare combustion efficiency result, which is a comparison of combusted and uncombusted carbon atoms basically out from the flare. Good. Now, before we go to the uncertainty assessment, let's have a brief look at the emission plumes, what they look like on a paper and how they look like when we actually measure them. So here you can see a very, very classical type of image. How does emission plume from this seemingly a power plant, how does it look like? And then on the other hand side, we have a typical graph on the Gaussian plume. Now, if we first take a look at the Gaussian plume. So Gaussian plume is very often visualized here on the left-hand side with this image, which shows that there is a source with an altitude, and from this source there comes a plume. There is an added altitude with the plume from the source, and then this plume has a normal distribution both in the y and z axis directions. Now, it's very important to understand that this is not actually how the plume looks like. This is actually a probability distribution on from where to locate the plume, especially if you are in the near field of the source, meaning that you are closer than a few hundred meters from the source. Moreover, this sort of standard theoretical plume behavior can turn into a different variances. It can, depending on the temperature gradient and depending on the wind conditions. So this Gaussian plume can behave as shown on the right-hand side, depending on the conditions. It can be a looping, coning, fanning, fumigating, lofting, trapping, or a neutral plume. Now, when these type of theoretical plumes meet the real-life circumstances and turbulent mixing, they start to form out as realistic plumes. So all these examples in the previous slide, they more or less assume a somewhat laminar flow of the wind field. Now, especially if we are considering the onshore measurements, we have trees, we have geography, we have hills, we have buildings, moreover. Of course, buildings exist also in the offshore, but otherwise the situation is slightly different. But this turbulent flow will cause turbulent mixing. And this is the first step where typically the modeling approaches can turn difficult for the quantification. So the uncertainty budgets and the assumptions needed for modeling in a case of turbulent mixing can be quite complicated. And this is the reason why typically quantification is based on the mass balance approach in cases where turbulent mixing happens. And here you can see some examples how, for example, consecutive buildings and the closeness of the buildings to each other in related to the wind direction affects to the type of turbulent flow that we see out in the field. So the closer they are to each other, this type of turbulent mixing can move from the isolated roughness into a wake or a skimming flow. Also, as a rule of thumb, the picture here at the bottom of the slide is something that we use internally also to train the field operatives on the as simply as the weather station location. So where to put the weather station to get an overview of the wind conditions on the sites. So here we can see how an building or trees with the altitude of H, what is the area of effects of these obstacles to the disturbed airflow field. Now, when all this is considered, the actual plumes may appear quite complicated. They may appear visually to actually go to different directions, especially in the near field. If we have a satellite view of some concentrations, this is an example of a methane plume seen from space here on the right-hand side up. And you can see that there is nothing Gaussian with this plume, what we see here. It's more arbitrary. Of course, it's going towards the prevailing wind direction, but other than that, it behaves quite with complicated manner. Here on the down, we have a cross-section that we measured from a plume. And this was a multi-source area, not too big, maybe 50 times 50 meters roughly of area that included 4 to 5 point sources. And these are just 2 consecutive cross sections of the plumes coming from that area. And from here we can see that the plume behavior is complicated. Now that we have a understanding of how the realistic real-life plumes actually behave, let's start to assess some quantification uncertainty. Because with the site level measurements, it doesn't matter if the measurement is done with a drone or with a car or with the dial or with the SOF. With all these methods, what everybody is measuring is the plume cross-section, basically, in one way or another. So all these principles, more or less, they touch all these methodologies, not only drone-based methodologies. Before we go further, let's just separate uncertainty and accuracy or error from each other. So uncertainty of a measurement result, that acknowledges that no measurement is actually perfect. And uncertainty defines like a group of values that could reasonably be linked to the actual result that was measured in those measurement conditions. So it's a population of results that might be true with the results that we have for that one individual measurement. Then accuracy is a difficult parameter in that sense that it requires the actual flow rate value, because accuracy is the closeness of the measurement results and the actual mass flow rate at the source. This can be also often referred as an error, which is the distance between the reported value and the actual value. Accuracy and error are something that are well present, typically in a control test release studies. However, in an actual production measurements, it's not typically available. And there, of course, then we have the comparison between the bottom-up and the top-down measurements. So as we already agreed, saw from the actual plumes, the real-world atmospheric airflow is complicated. And measuring compounds that this airflow carries, it's not trivial. It's actually quite dynamic. So in order to have a representative results and uncertainty that is meaningful to the result, there must be a link between the dynamic conditions during the data collection, during the measurement, and the result. And how this happens is that you actually have to master your entire measurement strategy in order to have that traceability to the conditions that were prevailing during the data collection. And this touches every single parameter that is used for the analysis. And for us, typical parameters that are used for analysis are not only the methane concentration or wind speed, but also wind direction, the location, altitude, and then depending on the measurement details, also other timestamp, of course, and so forth. So measurement strategy must be mastered in order to have, so that one can have a reliable uncertainty budget. This means that there are now two different approaches that I wanted to show in this slide. Let's start with this measurement strategy circle here. So in order to have the measurements in a traceable manner so that they can be reported in an understandable way, to be well documented and representative, when you're measuring your concentration, you need to have an understanding of what are the movement speed and spatial resolutions that you're using for that concentration measurements. And how do you log your three-dimensional location and timestamp related to the concentration measurements? And then how do you collect your wind data related to your concentration measurements? And what is the sampling rate of everything that you're measuring in order to have this data? How do these relate to the source area that you are trying to quantify? And what is the process phase in the process area? Is that process phase representative to the actual yearly emissions, or is it possibly an anomaly at the moment, what is happening over there? All this needs to be continuously handled during the data collection. And as we all know, it all starts with a plan. So we go to a site, we start to measure, we have a plan on how to do that. We start to do the work, then we stop because we observe that something happened. Maybe the wind direction changed drastically. We assess and react on what happened, and then we continue the data collection, making sure that the measurement strategy is continuously happening, and we are doing following the principles, where until we stop again, see what happened. So why do we need to stop and assess and react again before we continue? Good. Now, the factors that affect the site level quantification result uncertainty. In our case, we have chosen to follow the principles of the CEN technical standard 176601 for the concentration measurements. And the reason is that this is the only available technical documentation for sensor system uncertainty definition. It doesn't actually cover methane, but it's the best available standard for this task at the moment. So here, it means that we actually perform performance tests to our analyzers and sensors frequently. We also have an accredited reference gases in our laboratories, which we use to compare the small field calibration cylinders, which we can then send into the field. So in case we need to do a field calibration and test the calibration levels in the field, we have still the connection to the accredited standard gases all in the field with us. Then, in addition to this expanded sensor uncertainty, what affects the result uncertainty is the concentration level in relation to the system detection limits. This means that the closer we go to the system detection limits, the higher the concentration uncertainty actually is. So it's not a constant value, this concentration uncertainty throughout the measurement range, but actually the closer we go the detection limits, the higher also this uncertainty grows. Then we have the number of repetitions for the individual results. I have an example for this slide later. Then the repeatability of the detections in the data collection in these repetitions of results, connected to the stability of the weather conditions during the data collection. I am not saying that the stable stable weather conditions are the best for the uncertainty, but I'll say that the fact that if there is a prevailing wind direction helps a lot, because then we don't have to move around the site all the time when trying to catch the entire plume that we're trying to quantify. Then there is the variability of intermittent sources. How do they behave during the measurement window that we are when we are measuring? And then are there overlapping spread of emissions from sections that we have quantified separately? Here we also have an example of if we consider a single section, a single measurement. There is a reference measurement upwind, and there is a downwind measurement measuring everything that comes out from that section. How do we define the results on uncertainty for that single section? In a simple way, it is a subtraction of the downwind and upwind results and a sum of all the uncertainties related to them, those results. Then, if we are combining results, we have measured many different areas and we combine them together. It's then actually a sum of the measurements combined with, again, the sum of all the uncertainties. And here I have a real-life example of how that actually happens. This is a real, actual, results are real, but of course the site is anonymized. So in this site, there were 4 different area types, and 4 different source areas. Here the customer wanted to understand that from where the emissions come from. What is the fraction between different source areas? And this is quite understandable because if you consider reconciliation, it really adds value to have some sort of understanding on the sources, not only the single site level number. But here, just for a schematic example, area 4 was measured with these red lines that you can see here. So the wind was coming in this example from the up towards down. Area 4 was measured from the upwind side, from the downwind side, and there was a result. However, we of course now immediately see that the upwind side of area 4 is very highly and heavily overlapped by anything that comes from areas 1, 2, or 3. And likewise with the downwind from the area 4. So actually all the areas contribute to the downwind of area 4. Now, due to this wind direction and due to the results that we have there, what we also did was that we measured just a full site level upwind and downwind measurements. And the results were quite interesting because here in the table, you can see that if we combine the areas one by one, we got roughly little less than 7 kilos an hour for the entire site level emission with roughly 100% of our uncertainty. Now, this 100% derives directly from the overlapping of the emissions between the sections here. because every uncertainty is combined and then they start to accumulate to the final results. And now, if we compare that to the analysis where we measure the entire site as a whole, we can see that the actual mass flow result is the same, but now the uncertainty is 26%, which is quite typical in normal conditions, a typical uncertainty level that we get. So the conclusion here is that in quantification, losing the granularity improves the uncertainty. However, as we well understand, there must be a compromise between them. So because if we want to improve the site level reporting and get as much value from the site level quantification as possible, you should also have a visibility to the source areas and understand the fraction of sources, emissions from different sources. Because if the reconciliation shows that there are differences between the bottom-up and top-down measurements, having this visibility can help a lot on understanding that which sources are the reason, and are these sources, for example, variable that might explain. Of course, it's always beneficial to have the synchronized measurement of the bottom up and top down in order to mitigate as far as possible these variable sources and such behavior. Good. Here you can see an example of our own Airmon's experimental data on accuracy and uncertainty. Here on the upper image, this is just a direct analysis of the average error, so the average distance between the reported value and the true value from a control test release study conducted in Taddy Test Center in France. Here we can see that as the number of individual measurement wall repetitions increases, the error decreases. This is naturally expected, but from here you can also see that the reason we have as a rule that 3 repetitions is the minimum for an acceptable results can be understood when looking at the error behavior. So after 3 repetitions, the improvement slows down notably. Until 3 repetitions, always adding more improves the reliability of the results notably. And now error is not directly uncertainty. Uncertainty is the analysis of everything that I showed in the previous slide of the sensor error and the dynamic conditions and the repetitions from the individual results. And now if we consider from the same study our uncertainty behavior, here you can see the direct line is a 1-1 line of the actual true results. And then here we have our reported results with the uncertainty budget involved. And from here we can see that mainly the results, nearly all results actually, the uncertainty meets the actual real value, real release rates. However, there is an exception. In this exception, again, there is no filtering in this data. So in this test, there was a wind shift, and we have partial walls in that analysis, which explains why it's differing from this line. In a normal production conditions, such result would be neglected or reported as indicative because it was measured during non-conforming conditions. Now, what is the meaning of accreditation in related to the uncertainty assessments of the site level measurements? In Airmon's case, it means a continuous collaboration in research projects, which has been very essential for us to build a track of evidence to show that we are able to continuously improve in our not only results provision, but also in the realistic uncertainty assessments. We also have an in-house team of atmospheric physicists who work continuously to improve the methodologies that we use. But here you can see a quick glimpse of development during first years of the mass flow rate quantification, starting 21 from this GERG study, where we were heavily overestimating, moving towards the next year, where we were not too heavily overestimating anymore, and the number of results meeting the real value with the uncertainty budget was notably increased, but still not maybe as good as it could be. Whereafter moving forward, getting much better fits and also much better meets of the uncertainty budget with the real values. And then moving, of course, towards the image I showed you in the previous slide on where we are today. The laboratory accreditation that Airmon has, it includes measurements of such parameters as location, and then gases, compounds of carbon dioxide, for example, methane, and many others. Then wind speed and direction, ambient temperature, pressure, and humidity, relative humidity. And then the results that we derive from these. So direct results such as concentrations or wind speeds or wind direction, localization of an emission sources, which is of course an interpretation of data, mass flow rate quantification, then the combustion efficiency and the methane destruction efficiency from the flares. And when a service provider is accredited, it means that the reporting is audited and validated by a third party. It also means that all the methodologies that are utilized in order to collect the data for reporting are also audited. The reporting is quality controlled, representative, and traceable. It's transparent and as reliable as it can be. That means that it's accredited. And that was the presentation. I want to thank you all very much, and I hope there is a lot of questions related to this topic. I know this is a very, very hot topic and also very sometimes complex, often very complex topics. But I would also like to request some feedback from you. So if you would be so kind to just give half a minute of your time, you can take an image of the QR code. There is also a link in the chat of the meeting from where you can take the feedback study. But thank you all. Thank you very much.
Thank you very much, Matti. That was really clear and all nicely explained. I mean, the process and what to take into account. So I would really ask everybody to, I mean, we have enough time to either put the question in the chat or to raise hands. Yes, we have the raise hands. So let's see if, yeah. And then I think that you can unmute yourself. Yes, yes, Jeremy, please take a floor.
Oh, yeah, okay, my camera is working. I appreciate the presentation, Maddie. It was great. I guess you already covered it at the beginning, but I was curious if you could just maybe go over it one more time, kind of the differences between reverse dispersion modeling and the mass balance approach, please.
Yeah, definitely. Good. So in a way, the reverse dispersion modeling at its simplest form assumes the Gaussian plume that I showed you later on. So the theoretical plume shape. That is the most simple reverse dispersion modeling approach. And it's an inverse or reverse because what actually happens is that we are able to measure the concentration profile at the known distance to the source. And then we model that what has to be the mass flow rate at the source to explain this concentration at this distance in these weather conditions with the stability class that we have with this sunlight, that cloud coverage, this wind speed, and so forth. And this is the simplest example of the reverse dispersion modeling. Now, the mass balance. Here, the difference is that there is actually no modeling. It is a simple measurement of concentration and wind speed. And what it requires is that you are able to measure your perpendicular wind speed towards the plane or the wall or the curtain, however you call it, you measure. So with the drone, we fly this, we do a cross section of the entire plume area. And in each point, we measure the concentration and the perpendicular wind speed. And by combining that, basically making a surface integral of that, we are able to translate that information into a mass flow rate over that virtual plane that we just measured. So, and then of course, considering the reference of the upwind side, then you are able to separate that if you have something already entering your area, your source area beforehand, and then you can remove that from your entries. And this is basically the difference. So that's how the reverse modeling is truly a modeling, just turned other way around, whereas the mass balance approach, it's a direct measurement with no modeling assumptions.
Thank you.
Thank you.
So we have another question, please, Michael. Unmute yourself. Yes.
Can you hear me
Yes.
okay?
Yes, everything is fine.
Thank you very much. Matti, very well done. Thank you. This was very informative. I'm a lead auditor for MIQ for the company I work for. And you spoke right to my heart with one of the many things that we've urged some of the operators. There's this challenge, right, between logistics of obtaining the services to do the sensor analysis with drone or overhead and so forth. Then, of course, there's the conditions or the optimal conditions to take those measurements from, as you've really well addressed. So I fully advocate the same point of forming a very detailed plan on how you're going to collect the data. I mean, I can't emphasize that enough, and you did such a nice job with that. The question or thought I have is, coupled with the planning, is using the correct sensor type. So one of the questions I had for the analysis you've performed here, is that based on like tuned laser spectroscopy, so more of a passive sensor, versus an active LiDAR sensor? Because one of the things that we've done most recently, and I'm at this point, I'm not at liberty to kind of divulge the location, but I believe someone used the incorrect sensor. The conditions were not right, and the reconciliation was literally impossible. Led to no overlap. So I'd like if you could speak to that just momentarily about sensor type choice.
Yeah. Yes. So at Aramon, we have decided from the very beginning that we are sensor agnostics, which means that the hardware that we have actually developed, it's more like a universal sensor platform. And from the beginning, we have tested for methane, I think all the available different methane sensors that we could consider to be used in a sniffing method. So as a using a sample pump, extracting the sample, introducing that to a sensor, and measuring the concentration. So we have tested the NDIR, the metal oxide semiconductors, and then around 5 years ago, when the tunable diode laser spectrometers started to miniaturize, we tested them, and I would say that the combination of the detection limits and selectivity that those sensors provide is the reason that those have been mainly used by us since then. There are other options to more sensitive platforms also capable of measuring simultaneously ethane, because in some circumstances you need to differentiate between the biogas coming from next door from the natural gas you're measuring from the compressor station. So this can be utilized also. It's different type of laser spectrometer, but also basically a sniffer also. Yeah. We have tested these remote sensors, and I would say that we do believe that they have their correct place to be used, but only these sensitive laser spectrometers where you can go sub ppm detection limits and sub ppm resolution, those are needed in the site level so that you don't actually miss the meaningful leakages. That's per our experience.
Yeah. Perfect. Thank you. Yep.
Thank you, Michael. Thank you.
Thank you.
Oh, thank you for all the questions and explanations. So we have Jeremy once again with new question. So
Yeah, I have a bunch, but you're happy to go back the line after each one if that makes sense. But yeah, so I guess I was just a little curious about kind of the drone inspections themselves, if you are at liberty to talk a little bit about that. So I was just curious, a couple of things like, how long does when your drone site inspection takes, can any preparations you need to do, and if you're at liberty to say, how much would you charge for one of these drone inspections for a well site?
Well, from my side, I think I'm able to comment to part of the question at least. And the drone operations are something where always the local legislation is something that needs to be followed very closely. This is also the reason why we typically always work in collaboration with drone companies and drone operators that actually always have the local licenses to operate and access to the industrial areas in their jurisdiction. So we work with a lot of different companies directly, so that basically they provide us the drone operator, and we provide the rest. And how long does it take? Well, depending on a site, from a small site, we may talk about maybe tens of minutes. With a compressor sites, let's say roughly 5 to 10 hectares, for example, we are talking about 4 hours in total, maybe full working day. Slightly depends always on the wind direction, complexity. What do we see? How many source areas we find? So it really varies. Then in an offshore assets, this is I would say that the wind stability has maybe, in our case, has a stronger link to the length of the operation and not that much to the result reliability, because we can adapt when wind changes. However, if the wind changes in the middle of the measurement, we sort of have to start from the beginning. So it always takes slightly more time. So we try to reserve a few days when we are in offshore so that we can always find that weather window where the conditions are optimal. The pricing is more tricky question, and if you allow, I won't elaborate that. We are happy to discuss that separately afterwards. It really depends on, are we talking about a single survey, regular survey, 1 station, 5 stations, 10 stations, and so forth. So many things affect that.
Appreciate it. Thank you.
yeah, thank you. Thank you. I have a few questions actually, because after Jeremy and Michael setting the really expert questions, I have more like beginners questions. So that would be actually just to clarify. So in all this service which you are actually doing, so the different type of equipment is used, I believe. Because you mentioned drones, so I believe
Yep. Yes.
as a service provider you use them all, so
Yeah.
not just drone.
Yes. Yes, that is exactly correct. And actually, this universal sensor platform that we have developed and we use in our data collection, it's something that we can carry with a drone. However, drones for us are just a sophisticated ladder, if you may. So we can use bicycles or just an extension poles, or just we can collect data also by just walking. The measurement equipment itself doesn't know if it's carried by a drone or carried by a human hand. It just collects geospatial data with timestamp. So yes, we use the sensors for the data collection. We use weather stations. We have a stationary weather station, and then one, if we use drone, we have additional weather station on board of the drone too, so that we understand the local wind field better. Also used for the mass balance analysis, but we provide this all. So in case a site needs these measurements, Aeromon can provide the full service, so we can take care of the drone operator, unless of course the site already has a preferred drone partner, as larger sites typically always have. So from our side also, as we are sensor agnostic, so we can use whatever sensor technology is out there. In that sense, we're also drone agnostic, so we can also use whatever drone is available, just capable of carrying the payload weight that we have.
Okay.
Payload is being the sensor package, the analyzer, yes.
Yeah, in the meantime, I just see a question in the chat by Cynthia. So saying if there is a big difference in the measurement values gotten by two different models, which you explained in the beginning. I mean, models as such.
Yes. Just a second, actually. Now I took that away, but I will return this here. So, okay. So I hope you see my screen again.
Yes.
Here you can actually see that this image in the middle here is done with the reverse dispersion modeling. And whereas the last image here is done with the mass balance. And with both approaches, we can reach the same results. So there might not be that much difference in the actual results. However, the average error is higher with the reverse dispersion modeling than with mass balance. So that this is especially the case when the source area has even the slightest turbulent mixing taking place and happening there. So if nowadays we would use reverse dispersion modeling, we are very careful not to apply that to a source where the plume encounters the turbulent mixing. So it really needs to be an isolated plume that we can separate well from the surroundings. The difference between mass balance and RDM, reverse dispersion modeling, in the data collection side is that mass balance takes more time. So data collection for mass balance is slower than for the reverse dispersion modeling. So there is pros and cons. RDM might be faster in data collection, but then the uncertainty is higher, the average error is higher. Mass balance, data collection takes a longer time. You need to have a longer window of good weather, so to say. But then again, your results are more reliable than with reverse dispersion modeling. And this is the key difference.
Thank you. Thank you. And then one more question for beginners like me. So it's possible to measure kind of different gases in one go.
Yes, this is correct.
Okay. And then to see what is methane, what is CO2, and so on.
Yes, correct. So the universal sensor platform that we utilize in the data collection, it is quite typical that in these type of methane measurements, we have the methane sensor that we accompany with carbon dioxide and carbon monoxide sensor, because we use them in one and the same dual module. And then moreover, we can put in the non-methane volatile organic compound sensor in case there would be potential for longer hydrocarbons than methane on site. And when we are doing the data collection, all these different parameters are measured identically, similarly over the entire same area. So we can, in theory, carry, depending on the platform model that we use, 8 to 16 different gas components simultaneously. It really rarely happens, but in theory, we could do that. I think the record is around 8 parameters, and this is from a process industry side where there are very complex chemistries happening in the factory that we were measuring. But in the natural gas side, typical parameters for us are methane, sometimes methane and ethane, and then carbon dioxide, and maybe carbon monoxide and non-methane water organic compound.
No, thank you.
Yes,
and is there a different approach if you, I mean, with big industrial side? Okay, this is obvious. But if you look at the pipelines as such, I mean, transmission network, distribution network, or approach is the same.
No, it's not the same. So there is a difference, and this is also the reason why there is so big high importance in the measurement strategy, because the measurement strategy must meet the requirements of the site that you're measuring. It's completely different thing to measure a valve station to a compressor station, or 100 kilometers of pipeline to a compressor station again, or measuring about the LNG terminal or a offshore asset. So each of these require a different approach and different strategy.
Thank you. Thank you very much. It was really very clear, very informative, and I hope everybody enjoyed. We
Thank you
made
very much.
a
Thank you.
recording of the webinar. It's going to be uploaded on our website, hopefully with the slides, if Matti provide this to us, this package. Before you actually leave the meeting, check once again this form for feedback to Aeromont, and then with that, I would wish you to all very nice week in front of us, to thank to Matti once again, and to tell you that actually in 1 month time we have 2 presenters in the row, like for 12th of May and most probably 2nd of June, but you will be informed about that. So thank you very much.
Excellent. Thank you, Carolina.
Thank you,
Thank
Lena.
you.
Thank you, Matti.
Thank you.
Very much appreciate it. Bye-bye.
Thank you.